All right, we're going to talk about a couple more examples, problems in the sum of the force equations a little more in depth in this video. So let's talk first a little bit more about the inclined plane. So the inclined plane is just a fancy name for this ramp. We're going to put an object on it. And we have an angle on the ramp over here called theta. All right, if we draw in the gravitational force on the object where it's acting, and we extend kind of a dotted line here for where the normal force would be, the angle ends up being right here. So when we draw our free body diagram, also let me mention this is for a frictionless one. Our equations change when we have friction. We'll be talking about friction later this week. All right, so we have the normal force that's perpendicular to the surface, and we have the gravitational force coming straight down, which is equal to mg. All right, so now we need to look at where our x and y axis is. By the way, you would want to draw this on a separate force diagram than the one required for the answer. So if you're drawing a force diagram that's part of the question, or it's requiring you to, you need to draw a separate one to do the x and y axis and the components. I have limited space here, so I'm going to draw it on this one, but it should be a separate diagram. All right, so we can see from looking here, our angle ends up being right here. I do not know why I erased that. And so the only force not on our x or y axis is this gravitational force, okay? So that's the force we're going to break into x and y components. So we have a y component of the gravitational force that comes down the y-axis, and then we have a perpendicular horizontal component that is parallel to the x-axis. So this becomes my y component of the gravitational force, and this becomes my x component of the gravitational force. Then last year, I had you do the sum of the forces equation, so let's talk about what I mean by that. All right, we have to separate this into x and y. All force diagrams need to be separated into x and y unless they only have forces acting in the x direction or horizontal direction, or only have forces acting in the vertical or up and down direction. All right, let's talk about our rules for the sum of the force equations. All right, the first thing we need to do is it Newton's first law? Ooh, I can't spell today. Newton's first law? If it is, then the sum of our forces equals 0, or you could write it as the net force equals 0. Then, if it's not a first law, that means that it's probably a second law. If it is, then the sum of the forces equal mass times acceleration, or you can write it as the net force equals mass times acceleration. So we need to know which law applies before we can go on. And then you write your equations from the force diagram. So there's no equation. Ooh, what happened? No equation or formula for tension. You have to create it yourself. And make sure you keep x and y separate. You can't add a horizontal force to a vertical force without using Pythagorean theorem or some sort of trig, okay? All right, so this is something at rest, we'll call it. Oh, it can't be at rest. It's got to be accelerating because it has no friction. All right, this is accelerating, but it's accelerating only along the horizontal axis, not along the vertical. So for the vertical, the sum of the forces in the vertical direction are equal to 0. they're also equal to everything on or parallel to the y-axis. So we have the normal force going up along our y-axis minus that vertical or y component of the gravitational force. All right, so since the total force is equal to 0, but it's also equal to the normal force minus the gravitational force, I can combine those. So just like with money, I can have a $10 bill that's equal to $10, or I could have two $5 bills that also equal $10. So we find that our normal force is equal to this vertical component. Well, we have an equation for that. Since the gravitational force is equal to mass times the gravitational field strength, the vertical component is the gravitational force, or the mg, times, this is the adjacent side, so it's cosine of theta. That will give me that leg of the right triangle. So our normal force is equal to mg cosine theta. Unless there's another vertical force or component of the force, this will always be a true statement, and your normal force will always be equal to mg cosine theta. Now we go over here on the horizontal, and I said that was a second law problem. So it's mass times acceleration. The only force here on the horizontal part is this horizontal component of gravity. So that means my horizontal component of gravity has to be equal to my mass times acceleration. Just like we did over here for the vertical, we can make an equation for the horizontal, which is mass times the gravitational field strength. This is the opposite side of the angle, so it's sine of theta. So my mass times acceleration equals mass times the gravitational field strength times the sine of theta. Well, everybody brought the same mass to the party, so my mass is reduced if I divide both sides by the mass. And I get an equation for the acceleration of g, which is the gravitational field strength, times the sine of theta. And if there is no frictional forces or no other horizontal forces, this will also always be a true statement. But again, it has to only have this horizontal component of gravity acting on it and no friction. All right, let's try another example. This one is similar to the spider lab, but I'm only going to do one hanging mass. So the stationary hanging mass. The stationary, of course, means not moving, at rest, not accelerating. Okay? We're not going to talk about it as moving or not moving necessarily. We're going to talk in terms of acceleration. So accelerating or not accelerating. So let me draw the picture. All right, there's our diagram. I'm going to make this tension here FT3. I told you guys for the lab, you can draw your force diagram for this point right here where the angles are. That is absolutely fine. I'm just going to show you why we can do that and call that FT3 your gravitational force. Okay, so if I draw a force diagram for M3 with this as FT3, I get a force diagram that looks like this. I would then have to draw a separate diagram for these other two tension forces. And to make our lives easier, we just pretend that string's not here. We also, a lot of times, pretend that these strings are massless, which is not true. But if I pretend my mass is right here, then it makes my life a little easier, because then I just have the two tension forces that look like that, and the gravitational force pulling down. Okay, so we have angles here, just like we did last time. We need an x and a y axis. If you had to do a force diagram as part of your answer, you would do a separate force diagram for your components. Keep that in mind. All right, my angles in the picture are up here in this corner or this corner. Well, trig and geometry tells us that Let me fix my diagrams. Those must also be equal to the angles down here. So alternate interior angles. It's a theorem. You can look it up. But that puts my angles down here. Okay, so just like we did for the incline, we need to have our forces in the horizontal direction. And we need to do our sum of the forces in the vertical direction. So I come over here and I look at everything on or parallel to the x-axis. Well, I have a horizontal component for the tension force here. The reason we are doing components for the tension forces is because those are the two forces that do not lie on our axes that we drew. And it has a vertical component going up. So FT2 pulls to the right and up. FT1 pulls to the left and up. And we call those our vertical and horizontal components. I don't know why I have the one way over here. All right, so now when we go to write our equations, we first need to decide if this is a first law or a second law. And I just realized I put acceleration doesn't equal 0 here. That should have said acceleration does equal 0 because it's stationary. Oh, it's early in the morning. All right, so first law, that means the sum of my forces equals 0. My sum of my forces also equal these two horizontal forces subtracting from each other because they are in the opposite direction. So I have FT2x minus the FT1x. So now I can combine these two equations, and I see that the horizontal component of the second tension has to equal the horizontal component of the first tension. Well, now we can substitute in our trig equation. So these are the adjacent sides. So this one becomes FT2 times the cosine of theta 2, which equals FT1 times the cosine of theta 1. All right, there's not much else we can do here except for maybe solve for one in terms of the other, which I will let you guys do. That's part of your lab-based challenge. I'm going to come over here and help you write the sum of the force equations in the vertical direction. So in the vertical direction, I also have the sum of the forces or the net force equal to 0. The sum of the forces now are equal to these two upward components of the tension, FT1y plus FT2y minus the gravitational force, because that's the one going down. So I can combine these two equations together now. So that means FT1y plus FT2y, those two vertical components have to add up to equal the gravitational force. That makes sense because if I have acceleration of 0, all the forces added together, or force components going up added together, must equal all the force or force components going down added together. So now I get, these are the opposite sides. So I get FT1 sine of theta 1 plus FT2 sine of theta 2. Oh, I can't get my little 2 in there. That all has to be equal to the gravitational force. So sorry, I'm running out of space there. All right, so your spider lab is similar to this, especially the forces in the middle. The forces on the masses on the end, their force diagram should just have vertical forces only. Remember with tension, if we are doing massless strings and frictionless pulleys, that, let me draw a quick diagram here. This is the hint I gave the students in class. So I'll draw what the lab looks like. pen needs to be charged. All right, we had our pulleys up here. Oops. All right, so remember this tension all the way through that piece of string is equal. So if I'm calling this side FT1, I could also call this side FT1. The tension through this string is the same throughout. The tension through this string is the same throughout. Okay, that's the hint I will give you for the spider lab. If you have questions on that, let me know. We need to talk, actually, I'll make a separate video for circular motion. So that's all for this one. If y'all have questions, let me know. Have a great day.